Okay, so I'm back with the cholesterol data, and now we want to take a look at the gender and the amount of abdominal fat. You can see I've also got some coded columns here. This is an old data set I have, and it's not a real data set, so don't draw any conclusions from it, it's just a fake one. But depending on what software you use, sometimes you need to have things coded as numbers. The software won't use the words. In this case, I'm pretty sure Minitab is fine, but we'll give it a go and see what happens. If it fails, we can use the coded columns. So if I wanted to have a look at this difference in cholesterol between the genders and the levels of abdominal fat, I might first do a graph, and in this case I'd probably do a box plot just to have a look at all of it. So I want to do it with groups. So I want to graph the variables cholesterol, and let's do gender. Oh, what happened there? And obviously we can't see the average on the box plot because this gives us the distribution of the whole variable, but this is interesting to look at. It's possible there is some trend upwards for the males, a little bit difficult to pull out here. And the other thing we might want to look at first is the, again before we do the model, is the cholesterol with the abdominal fat to see if more fat around the abdomen is related to high cholesterol. And here we've got sort of a very clear pattern. The thing to note with these box plots is that if something has a very small effect, I don't know why that graph is doing that, it's flicking around. If something has a very small effect and the effect is only apparent once you adjust for the other variables in the model, you can't always see it, and that can be a little bit frustrating that you do a box plot and it looks like there's nothing there, but actually it turns out to be significant. On the flip side, you actually can get data where it looks like there's a difference, but due to perhaps a very small sample size or something else going on, even though it looks like there's a difference, it doesn't come up as being significant. So box plots and other graphs are always good for illustrating things, but we need to back them up with some analysis. So if we were going to do these by themselves, obviously we could do an independent t-test if we just had the two groups, the male and female. If we had these three levels of abdominal fat, we could do a simple analysis of variance. I'm not going to run either of those here. I'm going to look at doing everything all together. So back to my general linear model. Anything which is in categories, whether it's nominal or ordinal, you can add in as a factor. So we would put in our gender and we would put in our ab fat. Now it's probably remembered what we did last time, so with our graphs this is probably still ticked, which it is. Okay. So I'm going to look at a simple model here, and then in the next video I will look at adding in the interaction term between gender and ab fat. So the residuals are actually looking better here. They're looking a little bit more normal. So we still have this fairly random spread of values, of errors across the fitted values. There's no increase or decrease in variance. There are no obvious patterns here or curves. Something which I didn't talk about in the last video was this observation order, and you might be wondering why that matters. And this can happen if you're doing testing over a period of time. So let's say you were testing something to do with people, and you started in the morning, and then by the time you got to the afternoon you were finished, and perhaps you're testing something like, I don't know, like maybe serotonin or cortisol. It's possible that hormones or other things in the body do change over the course of the day. It's possible that the people doing the testing get tired over the course of the day. So sometimes you just want to have a look at, did anything happen over the course of the experiment? So you're literally just plotting them in order to see, is there anything happening from beginning to end. And this won't be important in all experiments or studies. It really depends on how it's been set up and whether or not the order has potentially any impact at all. In this case, because I've just got my fake island people, I'm not anticipating any difference here. So back to my normality, I'm looking to see for the first one, is it on a straight line? And it is sort of lining up. There's a tiny bit of a wiggle here. I don't think that's anything to worry about. And we can also look at the histogram, and this is looking more normal than the first time. It's a tiny bit skewed to the right, but we've only got a small sample size, so I'm going to go ahead and say that's probably okay. We don't have any residuals which are greater than 3 or less than -3, so I'm not too worried about outliers in this case. There's just a tiny bit of skew. So if we're happy with the residuals, now if you weren't happy with the residuals, if you thought there was a curve or something else in here, this is probably where in the real world you'd actually stop your analysis, and you might not even look at the rest of this output. You might go back and try and work out what was going on here first before you run your final model. In this case, if we can just go up and have a look, so we've got our general linear model, pull that down, and we're using weight, age, gender, and abdominal fat. So we knew that the weight was significant, so we sort of, I guess we would be assuming it would stay significant. The age, the p-value has changed. Now every time you add a variable into or take one out of a model, all the p-values will shift around a little bit because the model has changed, but it's still not significant. The gender is significant and the ab fat is significant. So the null hypothesis for gender would be that there is no difference between the genders once these other variables have been adjusted for. And the null hypothesis for ab fat would be that there is no difference in cholesterol for the different categories of abdominal fat once the other variables have been adjusted for. And we can see here that both of them are significant. Now this R squared is absolutely enormous. The highest is obviously 100%, that you can explain everything that is going on in your data. Our adjusted R squared has gone down just a little bit. I wouldn't expect that you would get an R squared this high for anything to do with people in real life. People tend to be quite variable, and it's very difficult to make really accurate predictions. This is on fake people, so that's why we're getting a really high R squared. So that would be, so that's the model. The last thing that we could look at is how would we build the regression equation here, and it has actually, it's spit out some different equations for the different factors here, so you can see them written out. You can actually include them all into one equation. It doesn't, I don't know, I can't remember why it doesn't do that for you. It's been too long since I used Minitab. So what we've got here is that cholesterol is equal to, on average, 3.5 plus this little adjustment for your weight, so 0.036 times your weight. Age we're going to ignore because it's not significant, but later we might take that out of the model. The base model is set up for males, and we've got a little adjustment downwards for females, so subtract 0.05 for females, and for abdominal fat the reference level appears to be high abdominal fat. If you have low abdominal fat, you get this extra adjustment downwards, 0.04. If you have some abdominal fat, you're getting an adjustment upwards, a tiny little adjustment. I can't remember what my levels were. Low, some, severe. That's interesting. It's not quite significant, but that's actually saying you're getting a little bit of an adjustment upwards for some abdominal fat over severe. I wonder if that will stay that way if we add in the interaction term. So that's a little bit curious that you'd have slightly higher cholesterol with some abdominal fat rather than severe. But if we fix up the model, it might not stay there. So if I was running this model, I would probably take out the age because we've seen now that it's not significant. So if I just do that here, I can just delete it. Again, the residuals look fine. And we've got the weight, gender, and the ab fat are all significant. And we do still have this slight adjustment for ab fat. Oh, that's interesting. So the general technique, there's a few ways you can go about building these models. You can start off with one variable and you can add them in one at a time. If it's significant, you keep it in. If it's not significant, you drop it and you try the next one. And that would be a forward stepwise regression. The other thing you can do is start off with all your variables, and then you can take them out one at a time if they are not significant. So you would put everything in. If the one with the highest p-value, you would take it out and run the model again. But because the p-values change every time you run a model, you should only look at one at a time rather than taking 2 or 3 out at a time, because the other p-values may change. So this model is not quite finished. If I was going all the way with this, I'd also add in an interaction term, and I will do that in the next video.